Yeah, so first I want to clarify that if you've got up on a pedestal, AstroPy and the affiliated packages is this nirvana where every example in the documentation works and there are unit tests for absolutely everything. Stuart just indicated the actual truth of that. So our next speaker is Monica Bobra from Stanford University, talking about using machine learning to predict solar flares.
Hello, is this on? Yep. Okay. Yeah, so switching course entirely here, totally different topic. Yes, I'm talking about predicting solar flares using machine learning, and this movie that's playing right here in the background and kept starting over and over shows a flare that we observed in September of last year, which turned out to be the largest flare that we observed over the last 12 years. It's from this region right here. It's about to flare. There you go. And I'll be referring to this event a little bit in my talk. So I know that we've talked a bit about machine learning, and I can tell that there's some real experts in the room, and there might be some people who haven't played around too much with machine learning packages. So I thought I would start at the very beginning and ask, what is machine learning and why is it useful for us? And I thought I would answer that question by way of an example. So this is an image of a spiral galaxy taken by the Sloan Digital Sky Survey, and SDSS took 1 million such images between the year 2000 and 2008. And after they had done this observing run, they realized they had a problem. It would take them years to classify all of these galaxies. So instead, they came up with an idea that maybe many people in the room are familiar with called Galaxy Zoo, where they took all these images and they farmed them out to citizen scientists all over the world who classified these galaxies and submitted the answers back to the SDSS team. And as a result, they were able to classify all these galaxies in just 3 weeks. And this is what the co-founder of Galaxy Zoo, Kevin Skowinski, had to say about it. We had succeeded in creating the world's most powerful pattern recognizing supercomputer, and it existed in the linked intelligence of all the people who had logged onto our website. And this global brain was processing this stuff incredibly fast and incredibly accurately. And this is exactly the concept behind machine learning. So in the Galaxy Zoo case, the astronomers trained the citizens how to classify the galaxies. And in the machine learning case, the astronomers trained the machine how to classify the galaxy. So in this way, machine learning doesn't abstract the scientist away from the scientific process, but rather enables the scientist to do better research with more useful data. So how can machine learning be useful to us, astronomers? There are a few classes of problems that are particularly well suited for machine learning. One is, for example, classification, classifying different types of galaxies in image data. A second is event detection, for example, detecting supernova and photometric data. A third is clustering, or determining from a wide variety of characteristics how many groups your data fall into. And one example of that is clustering different types of line profiles in spectral data. And a fourth is prediction, so predicting, for example, the occurrence of solar flares. And in this talk, I'll talk about these two, and I'll go through an example of how we can use machine learning to predict solar flares. So how do we go about using machine learning to predict solar flares? So this is an image of the magnetic field at the solar surface. So the white bits are where the magnetic field is coming out of the page. The black bits are where the magnetic field is going into the page, and the gray is generally zero, no field. And we know that solar flares come from areas of concentrated, strong, complex magnetic fields, which we call active regions. So our first step is to identify these active regions. And then the next step is to characterize features of interest associated with these active regions. So this is an image of the X-ray solar corona, so 10,000 kilometers above the solar surface, and you see all of these different features. And in particular, with this active region, you see this S-shaped feature. And from previous statistical studies, we know that when we see an S-shaped feature in the solar corona that is cotemporal with a strong and complex magnetic field structure on the solar surface, these conditions are sort of ripe for producing a solar flare. But of course, if you're working with data from, for example, the Solar Dynamics Observatory, which takes 1.5 terabytes of data a day, which takes an image like this every 3 seconds and has been doing so for the last 8 years, we can't exactly look at every single image and figure out, how many of these have S-shaped structures in them and how many don't. So one way we can solve this problem is by using a machine learning algorithm. And one way you can use a machine learning algorithm is by implementing this structure called a convolutional neural network. And you can call these kinds of machine learning examples from PyTorch, Keras, Theano, and there's a really good example of how to use PyTorch at that URL there. So anyways, what is a convolutional neural network? How does it work? Why do we care about it? What does it do? So this is how it works. You start with an image, and the algorithm then convolves it with a filter, thresholds it, downsamples it, and vectorizes it to create a total feature vector. And you might think, okay, this is a series of really simple image processing steps. Why does this work? Why is it so kind of en vogue right now? And the reason is because now we have a lot of data. So maybe 10 years ago, we had like hundreds or thousands of images of the solar corona from any given instrument. But now we have hundreds of millions of images of the solar corona that we can use to train these models. So we train these models and learning happens here at the filter stage. So this algorithm is choosing filters such that the total feature vector of an image that contains an S-shaped region looks drastically different to a total feature vector of an image that does not contain an S-shaped region. So in this way, you can use these algorithms, sort of sort through your data, pick out the images that you care about, and use it to create a rich, complete event catalog in a way that is reproducible and scalable and fast. So now that we have all these features, we associated with active regions. We know whether or not there's an S-shaped structure in the solar corona. We may have other features like the size of the active region, the amount of magnetic flux going through the active region. So you have all these features. Now we're going to use them to predict solar flares. So how do we do that? Okay, the next step is to define the task. So this is a plot of the integrated solar X-ray flux as measured by the GOES satellite. On the y-axis is flux on a log scale. On the x-axis is time. The two different colors are two different wavelength bands. And when the integrated flux exceeds 10 to the minus 4 watts per meter squared, we call that a big flare, an X-class flare, and you can see that there was one right here. So our task is to try to figure out whether we can predict this flare up to 24 hours in advance. That's what we're trying to do. So how can we go about doing that? We can use another machine learning algorithm to accomplish this task. And in this particular case, we could use a support vector machine. And these kinds of algorithms can be accessed through the scikit-learn library. And I cannot say enough good things about the scikit-learn library. I think it's excellent. It's really well documented. It's got a lot of examples, and also it has a unified API. So if you wanted to, any machine learning algorithm that you wanted to call would be called in the exact same way through scikit-learn. So I think it's an excellent library. Okay, so how do we go about using these features to predict flares? So imagine that you have a two-dimensional feature space, and the blue circles are active regions that flared, and the red X's are active regions that did not flare. And imagine that the x-axis is the area of the active region, and the y-axis is the total flux going through the region. So you could interpret this plot by saying, okay, if you have active regions that are kind of small, really compact, but have a lot of flux going through them, they're likely to flare. If you have active regions that are large, diffuse, maybe don't have that much magnetic flux going through them, they're not likely to flare. And all the learning algorithm is doing is drawing a line between these two classes. And it's drawing that line where the distance to the nearest positive and negative example is maximized. But of course, we don't just have 2 features. We could have like 47 features. And in that case, the algorithm is not drawing a 2-dimensional feature space. It is creating a 47-dimensional feature space. And is not drawing a line that's separating the 2 classes, but rather a nonlinear hypersurface that's separating the 2 classes. And then when you have a future example for which you do not know the answer, you can plot it in this. The algorithm plots it in this 47-dimensional feature space, figures out which side of the decision boundary it's on, and based on that, issues a prediction. And we have done that. And in this way, machine learning algorithms can sort of identify relationships between features that are complex, that we couldn't see visually by eye, and that we couldn't learn from simple statistical relationships. And so we have done that, and most importantly, we have taken all of the code that we've written to do this analysis and made it available in an IPython notebook, which I just updated for PyAstro, so it has all of the most recent libraries and everything in it. It should run. I just tested it. And you can look here for an example of how to use machine learning with solar data. And if you're looking for an example of how to use machine learning with other astrophysical data sets, the AstroML library is a good place to start. There are lots of examples, and they've also written a book called Statistics, Machine Learning, and Data Mining in Astrophysics. So I hope that this is a good place to get started, and if you have any questions, feel free to ask.
And we've got plenty of time for questions.
Thanks, Monica. I was just wondering if you have any experience and knowledge of how likely these methods are to force categorizations if there aren't ones that are really there. Is it programmed to find them even if they're not there?
That's a pretty big problem in machine learning, so you can overfit the data. So for example, if you go to this and instead of a line, if these populations were closer together, the decision boundary might be this like weird shape that's only valid for this case. And if you added more data later, you know, it wouldn't follow that behavior. So there are ways to sort of test to see if you're overfitting your data. There are lots of different cross-validation methods people use to test to see if you're overfitting your data. And that's a good example. And I just also wanted to mention, which I didn't mention in this talk, but there's a library called Lime that people have come up with, this also in Python, that sort of helps you interpret what the algorithm is doing, because that is one criticism of machine learning, is that it's kind of a black box. Some of the algorithms are kind of a black box and you don't know what's going on, but people are sort of trying to address that problem, and this is a tool that sort of helps you look inside the black box, if that's what you want to call it, and see what's going on.
And just a quick follow-up question, if you go back to your graph,
Yeah.
Do these methods sort of give a binary decision, or you could imagine there'd be some gray area or uncertainty in that middle region? Can it give you back a confidence measure of how sure it is based on where your data is on that graph?
Yeah, so, well, there are lots of different ways you can tell the algorithm to draw this line. One thing that I didn't address, and which is a problem for all of us in astrophysics, whether we're doing solar physics or anything else, is that we always are dealing with class imbalance. So for example, there are more cases where there is no supernova than there is, or there are more cases where there's no flare than when there is. So you can tell the algorithm how you want it to penalize a wrong classification. So you know, this is such a beautiful example. I just drew this, right? This is not how our data ever look. So there are going to be misclassifications, but you can kind of figure out how many are acceptable to you based on whether or not a false positive is worse or a true positive is worse, and tell the algorithm where to draw that line. So it's not like there's a gray area really. It's more that there's an overlap, and how many misclassifications are you willing to live with?
Can you just pass the mic over to the...
Great talk, Monica. So quick question here. I missed if you were using the time series of images that you're getting from Soho, or are you just looking at features image by image?
Features image by image.
So that raises another question, right? Because the sun, these spots are presumably not constant in position on the sun, and they move around, and so their apparent size and things are changing over time. How do you deal with that in your neural network?
Yeah, so this was kind of our initial approach. And so there are lots of different ways we could parameterize it. We could say, how much has the flux changed in the last hour? Or what's the slope of, or we could fit it with some sort of polynomial or whatever and figure out what those coefficients are as compared to the plot of the flux over time for an active region that didn't flare. So there are lots of different ways to take it into account. But we track one active region. So the issue is to just predict it, you know, some time in advance. So it's okay to sort of take that snapshot. Can we take that snapshot? Because that's what space weather forecasters are looking at. Just the sun right now. Can we figure out what to issue as a forecast based on the sun right now?
Okay. Is there any questions in the room?
So I just had a quick question of, like, how well is this working?
This is working pretty well, but you know, I don't really. Okay, so to answer that question, I'll sort of give some background, and Sophie can kind of jump in here too because she knows a lot about space weather prediction. But NOAA has a space weather prediction center, and they issue their predictions based on user experience, lookup tables, and statistical models, like one statistical model, particularly called WSA NLIL. So they're basically just using intuition. So this does better than that, but that's kind of a low bar. So it's not like it's so amazing. There are a lot of improvements to be made, but I think you know, I can make the strong argument that this does better than that. So it's worth looking into.
This is Sophie. So in operational forecasting, you kind of have to beat climatology. So if you look at entire solar cycles worth of data, and you know, maybe you take an average over it or something like that, you need to be much better than climatology. So what we need to do to get machine learning into operational kind of use is to show that it's much better than what they're currently using. So that's the key right now, is to show that. A lot of operational centers want to use something easy and robust and reliable, so that's why they use the really simple lookup tables. So I think in the future these things are going to be brought in, but they haven't quite got there yet.
So yeah, the question was, how much better is this than just predicting no flare all the time? Because most of the time there are no flares.
Yeah, I mean, that's a... So you can imagine computing the accuracy of something. Like you can do it with earthquakes, for example, since I live in California. I could just predict, I could go to work every single day and predict there's going to be no earthquake. I would be right, like 99 point whatever. You could say I'd be right, 5 sigma. It's a great model just to come into work and saying, but it's not telling us anything. There's no information in that model. So instead, accuracy is, you know, we don't use accuracy as a metric. We use other metrics. We say, okay, we can calculate a skill score. How much better can you do than predicting no all the time? How much better can you do than whatever, predicting randomly? And so we have computed that, and there's a lot of discussion about skill scores. And so we have predicted, we have calculated what we call a true skill score. Sean Bluefeld came up with that, so I don't know, maybe you know about that paper. But anyways, it does much better than predicting randomly. So.
All right, with that, let's thank Monica again. For the remote folks, we will get your questions to Monica later today, who hopefully